Hello everyone, welcome to the second lecture of week 12. So we started discussion about model interpretability, and in this lecture we will see how we can extend that to multilingual scenarios. Okay. So we'll talk about various interesting topics like what is our understanding on how do multilingual transformers really work. So we'll come back to the discussion about language specific neurons. How do we identify neurons that are responsible for specific languages? And we will give some hypothesis that was there for multilingual workflow. So if you have a query in a different language than English, how does the language model that has been trained primarily on English but also in other languages work? So this is, this picture is a continuation of what we were discussing about logit lens, but this is from a very recent paper on do llamas work in English, right, on the latent language of multilingual transformers. So what you are seeing here, so if you just look at the picture, you are seeing again some predictions across layers. So these are layers, and you are trying to project using maybe the tune lens what is the word that you will predict from that hidden layer, right? And you see, it is going to a language quite later, right? And that's what was the finding. So the model used was llama 2, 7 billion, and you apply logit lens to any intermediate layer, so and you get the next word distribution, and you show the final, the top one output per layer. Now what was the task, what was the input here? So they were doing translation, so they were giving word translation only, like using in context examples. So they say, okay, in French this is the word, in Chinese this meant Chinese, in Chinese what is the word? So even the French, saying French and Chinese, they were writing in the French and Chinese. So this is the French word, and then you have the corresponding Chinese word, right? And they were giving French, Chinese also. This is the French language, this is just the Chinese language, right? This means Chinese. So they do it for certain examples, and then they started seeing, okay, let's predict now. So this is saying after Chinese, what would you predict? And so after that, what you were predicting, so this should decode the English word flower, right? So you want to predict the word flower here, but in Chinese, because you have to convert into Chinese. And what they found, for example, interestingly, it starts predicting it in English first, right? So do the work in English, they start predicting the word English before it predicts it in Chinese, right? It predicts in Chinese later on, but predicts in English before. So that was very interesting finding, right? So you have to predict the next word, the concept you are able to identify, but you are identifying in English, right? And before you are spitting it out in the language than which you have to. So they defined certain tasks. So we will just briefly discuss those. So one was the translation task. So you will have a non-English word like French word, and you want to translate into Chinese, like here. So you will give these examples in context. So this is in French, particular word, and this is Chinese, the corresponding translation. This is the translation in Chinese, and this just means French and Chinese languages in the script themselves, right? And you give these examples, but for the last prompt, as we do in context learning with few shot, you give the input only, put Chinese, and let the model predict the word, right? And that's why you see this becomes a very simple task, because you are doing word by word translation. But here at what layer it is able to make this prediction, what is the corresponding Chinese token. And to contrast, they also did a simple repetition task where you will simply put it in Chinese. So Chinese, this again Chinese, the same symbol. So model is learning simply to repeat that token. It's not thinking much, it's just repeating the token, right? You just have to repeat the token. So if you have to translate, you have to do certain tasks. You have to get the corresponding alignment, that what is the corresponding embedding space in Chinese, what is the corresponding word. But here you are just repeating the same word. So, your thinking will be much limited here, your reasoning task is much limited. So, is the pattern for the model different across say repetition task and translation task? And that is what they found. So, this is so what they do for every task, they have the correct Chinese token and they also know what is the correct English token, right. I mean, so you have this word and you know flower is the correct English word and you have a correct Chinese word also. So, they start saying from each layer what is the probability of predicting the correct English word and what is the probability of predicting the correct Chinese word, right. So, this is across layers, and interestingly what they find, let us say this translation task. So, say up to 15 layers, right, you neither have a good probability for English nor good probability for Chinese, right. So, that means possibly the model is just performing, I mean just using the embedding and making a better and better representation, it is not trying to do the task up to the 15th layer. But suddenly after 15th layer, you see there is a jump in the probability in translation, especially for English token, the correct token. So, they start predicting English with a higher probability, right. And Chinese also starts increasing, but slowly. I mean until you reach nearly the end phase, right, and where you start giving the Chinese token a higher probability than the English token. That was very, very interesting. So, across models with different layers, so very similar phenomena was seen, that you have the initial layers where you are building representation, right, but not trying to predict the token, but then the middle layers English take predominance. So, you start generating the output in English, but in the final layer you will spit it out in the language of your input, right, the language in which you wanted to output. So, English has a sharp rise followed by a decline, and Chinese slowly grows, and after a crossover with English it spikes in the last 5 layers. So, that is what was very interesting about how these multilingual models work. Yeah, while if you contest with repetition task where you did not have to translate, Chinese even does better. I mean the probability starts increasing already. So, it does not go through English so much. So, even the earlier layers had a high probability for Chinese compared to English, right. So, this is again a very nice contrast depending on the task complexity. So, if you do not have to think, you are just doing things in Chinese, but if you have to really think, you are going to English space and doing the thinking, coming back to Chinese. Okay, and then based on this very interesting finding, they clearly identified 3 phases in the LMs. I mean these phases are divided across layers. So, you have first phase that goes say in 80 layers model up to 0 to close to 40 phases, where what you are doing, you are building good token representations, right. So, if you see the language probability both for English and Chinese is very low. Then comes the second phase, which is where they call the concept space, where you give higher probability tokens in English, you try to think and get the final output. So, this is your concept space. So, you start with a building representation, then you have the context space. Finally, you are predicting the concepts in the chosen target language, that is your final phase 3, right. And so, you very nicely, I mean they identify these 3 phases in which the processing happens in multilingual models. Now, they also tried putting other things like entropy. So, of the distribution which is very, very high initially up to 40 layers, but then there is a sudden drop, it is like a change of phase, and then you start having a very low entropy of the probability distribution. Okay. Now, coming to another paper, this was similar ideas, but I mean, so they were trying to see are there some language specific neurons that we see in the models. So, we are talking about multilingual models and we are doing multilingual task. Are there certain neurons, certain units that are more responsible towards certain languages than others? So, here is an illustration. Suppose this is your input. So, when you are happy, clap your, I mean this you are giving in English, or you can give in other languages, right. So, English, French, Chinese. Now, what they see, suppose you are passing this input in English or French or Chinese, there are certain neurons that are language agnostic. So, similar to phase 1 that we saw. So, they will do processing, they will build a good representation, right? They are not responsible for the language part as such, right. Now, after that phase or after that those neurons, there are certain neurons that are responsible for different languages. Like there are certain English neurons that will process this English text, there are certain French neurons, there are Chinese neurons that are processing different languages, right. And you may even turn these off, like you may turn off these Chinese neurons and suddenly you see a huge drop in the performance. So, performance drops immediately when you turn off Chinese neurons and try Chinese language input, right. So, that gives a much more evidence that there are language specific neurons involved in the model. Okay. So, this is again how do you find these language specific neurons? I mean, we will see what is the method that they identified. And the method is what they called as the LAPE score, language activation probability entropy. So, what they do there? So you take an LLM that is already pre-trained. Now, you feed that with multilingual text. So, sometimes you feed it only with say Chinese sentence, sometimes French sentence, sometimes English sentence, right. But a sentence will have only one language, right. You will feed it with one language at a time. Now, it has multiple layers. So, let us say I focus on the ith layer. In the ith layer, again there are many neurons. So, let us say I focus on the jth neuron. Now, this can be anywhere, right, and this can be any neuron, but here they focused on only the neuron at the feed forward layer, right. Of course, they had more experiments where they, I mean, some papers had more experiment where they focus on MLP and attention, but here they are focusing more on the feed forward layer neurons. So, what you will do? So, you will take the ith layer and take the jth neuron, right, from this, and you compute what is the activation probability of this when it processes the text in language. Okay. So, in this the weight W1, so they will particularly took this W1 weight. So, you will have different neurons there, and find for any neuron here in this particular weight matrix, what is the probability that this is activated. Now, how do you find that out? What is the probability that this is activated for a particular language? So, you say okay, I will pass this language K, say I pass language Chinese, and I find out where all this the jth neuron, I mean this HI W1J W1I for the jth neuron, wherever this is greater than 0, right, and you can count it across multiple sentences. So, let us say I pass 10 sentences for language Chinese. I compute this, I mean after applying HI W1I activation function, is this greater than 0? So, let us say out of 10 sentences 0 for 7 times. So, my probability is 0.7. So, that means this particular neuron is activated 0.7 with a probability of 0.7 for this particular language, and this probability may be different across languages, right. So, you can what you can do, you can compute this probability for all the languages, right, and then you normalize them. So, you normalize these and you get a distribution, right. So, what is the probability of this neuron getting activated for this language, that language, and so on. And then once you have the distribution, then you compute the LAPE score, that is for the ith layer jth neuron, what is the entropy across languages. Now, what would you guess? I mean, if a neuron is language specific, it will fire only for specific languages, but will not fire across languages, right. So, it should have a high entropy, right. So, so they compute the entropy score, right. I mean, so if it is uniform, yeah, if it is uniform, then you will have a very high entropy. So, if this LAPE score is high, that means across languages I have very similar probability. So, across languages very similar, but that is not language specific. So that means what we are looking for is a low LAPE score, because I should be high, LAPE score should be high for one language. I mean, the probability should be high for one language, but not so high for other languages. Then the corresponding entropy loss will be lower, right. So this low LAPE scores will be what is known as the language specific neurons. So they use this method to identify language specific neurons, okay, and then they say, okay, what if I deactivate the language specific neurons? So how do you read this table? So you take the ith row. So let's say this is the ith row, and this is the jth column. And what you will see, so suppose I perturb ith row and the language in the ith row. That means I'll deactivate the language specific neurons for Chinese. I deactivate Chinese neurons, whatever I identified using the LAPE score. After deactivation, I will now try on this jth column. In this case, this is also Chinese, and see what is the perplexity. And they say if there is an increase in perplexity, that means the performance is going down, right? And they see, okay, there is a perplexity increase if I deactivate the Chinese neurons for Chinese, right? And this also happens for other like Japanese. Like if I deactivate Chinese neurons even for Japanese, you see a performance drop, a perplexity increase. And this is some sort of symmetric, like if you deactivate Japanese neurons, you get a perplexity increase in Chinese as well as in Japanese. Okay. Then then they also try to analyze. So let's say they took this llama to 70 billion model, and you have a question in the simplified Chinese. That's like your question in Chinese. This is what it means. You are a mountain climber reaching the summit of Mount Everest. Describe your emotions and the view. That's your question, and this is your normal output. If you do not change your model anything, it gives an output in Chinese, right? And this in translation means I am a climber who has reached the summit of Mount Everest. I am very excited and proud. That's typically the answer. But what if I deactivate the Chinese specific neurons here? So after deactivation, this is the output, and you see, in between it is also producing an English output, right? It's not just giving a Chinese output; it's mixing with English output, right? So that's a problem. So you remove language specific neurons, and the performance is degrading on that particular language. And now there's another paper that tried along very similar lines. So this was how do large language models handle multilingualism. So they gave another hypothesis for multilingual workflow. So let's say we have a query not in English, and I want to answer that query. So what they say, fine. So you have this 3 phases again. So in the first phase, you will try to understand. So you will interpret the query, understand the query. That will happen in multilingual, right? After you have done a good representation, you have interpreted. Now you try to really solve the task, like translation. Remember translation? So we solve the task, and this solving the task, the thinking happens in English. That was their finding also. And while they try to differentiate between the two things, even in the middle layer, that is, there is something happening as self attention and something happening at the feed forward layer. So in the self attention layer, you have thinking happening in English, and feed forward layer, you are using the knowledge. You are getting the knowledge. That is the multilingual knowledge, right? And that you get this representation. And then finally, in the generate phase, you generate output in the language, the multilingual. So you come back to just multilingual generation. So they give some more, some better, much more elaborate picture on how multilingual queries really work in multilingual LLMs. So for example, this is a plot that they show. So they test with various non-English queries, and you again apply logicalness. So you decode various hidden embeddings of each layer, right? You project them to LLM's vocabulary, but they don't just see the final token distribution. They say, okay, when you project into vocabulary, let me only see the English vocabulary space versus the Chinese or any other language vocabulary space, right? English and non-English vocabulary space. Now, do I see that the particular vocabulary is taking the much more probability mass than others, right, across layers? So this is just the probability, right? One it's highest. So dark means much higher. So, what they found again, like as per the phases, that yes, in the initial phase, in the initial few layers, the processing happening in the non-English, the multilingual, right. So, they have the highest probability. Then there is some change, and then in the middle layers, the thinking is happening in English. So, you have a high probability to English, but then it slightly goes down until you have again a phase change, and in the last few layers, you have a higher probability of the non-English tokens, right. Okay. So, then they identify another method for finding language specific neurons. So, they say, okay, let us say we have the ith layer. Okay. Now, take a particular neuron in this ith layer, say an I. Now, this they now further said it can either be in attention layer or it can be in the feed forward layer. Now, how do I quantify its importance in processing the input, right? So, they say, okay, we can do very simply. They say, okay, so let us say we have the layer input Hi. Now, I apply to Hi, I will first apply the self attention, then I apply the MLP, right, and then I get the Hi plus 1. So, they say, okay, my neuron can be either in attention or MLP. So, I will run my model twice, once by deactivating that neuron. So, this is when this minus that neuron is deactivated, and once like normally, and I will find out how is the Hi plus 1 different from Hi when I deactivate the neuron. That will tell the importance. This is just the absolute score. Now, if this neuron was specific to the language, this change would be above a certain threshold, right. I mean, so if this was actually important for the language, by turning it off, I will see some huge difference across the representations from Hi and Hi plus 1. But if it was not important for the language, I would not see much difference across the representations. So, they say, okay, what is the difference across two layers when I turn off a particular deactivate a particular neuron, which can be either in attention or MLP. And then I do it for a corpus, multiple sentences in the same language. So, it should happen consistently across languages, right, across sentences in a given language, right, and then only I can find this is important for that particular language. Okay. So, just to recap, I mean, what they will do, they will take a corpus for multiple languages. For each language, they will have multiple sentences, and they will see for a particular neuron what is the activation if I remove that versus I keep it, and if the difference is above a threshold for all the sentences in that language, I will say that this is an important neuron for the language. And then they say, okay, so yeah, they feed a corpus in a specific language and identify neurons that are consistently activated, and they are responsible for processing queries in that language. And now they say, okay, fine, then once we identify these neurons, we can also verify what happens if I turn these off, like, and do a particular task. And they say, okay, they actually tried this across two models, Vicuna and Mistral. This is the original model, and they just deactivated 0.13% of the neurons. So, they say, okay, I can also try deactivating some neurons randomly, right. What happens then? This is deactivate random, and you see performance drop, but not so much. I mean, this is nearly same. But if you deactivate language specific neurons, same number of neurons, you see, I mean, there is a drastic change. So, this nearly drops to 0. There is no performance at all. So, that means this language specific neurons were much more responsible for performing this multilingual task. And then they had this again, because they could identify the neuron was within feed forward network or attention structure, they could see how the LLM is really processing. So, what they identified, that you see again you can see three phases. So, first of all, it is able to identify. So, what is the number of language specific neurons? So, you have the initial layers where it is happening in multilingual. So, you have a large number of language specific neurons, right. So, this is slightly in contrast with the previous paper, which said there are no language specific neurons early on, but they said, okay, so lot of things happen in multilingual initially, right. But then suddenly, specifically in the attention layer, the number of language specific neurons decreases drastically, right, but does not happen so for feed forward. And that is why they say, because in attention the thinking is happening mainly in English. So, they are not so much language specific neurons there. So, they are typically working in English. So, you do not have anything specific for a language that happens there. But for FFN, you have a consistent behavior, right? I mean, so that is why they had a distinction in the middle layer. So, the thinking is happening in English, at the same time the knowledge retrieval, right. So, you are getting the multilingual knowledge that is happening in feed forward layer through the multilingual neurons, and then finally you generate. So, even this the attention layer also has an increase, right. So, finally the model are able to generate the responses that are aligned with the user query's original language. So, this again gets a very interesting idea, that you had 3 phases where you think in multilingual, then process in multilingual, get a good representation, then you start thinking English, but all at the same time you retrieve knowledge, multilingual knowledge through FFN. Now, are FFN suited for retrieving multilingual language? So, there is another hypothesis behind that, right. So, this is, can feed forward network be used for retrieving knowledge, right. So, this is what we will see in the next lecture, right. Again, a continuation of interpretability, we will see how feed forward networks are good for retrieving multilingual knowledge, right. So, we will talk about that, or in general how do they retrieve knowledge, right, from the training. So, yeah, so we discussed in this lecture various efforts on multilingual interpretability, continuing from what we were doing in the previous lecture, and various papers that we have cited in the slides are the good references from which you can read more about it. But yeah, it is an emerging field, and you will get to know more research papers coming out. So, yeah, we will continue the discussion about interpretability. We will focus on the feed forward layer in the next lecture. We will talk about this, how they can really retrieve the multilingual or general knowledge, right, from the training. Thank you.